Hello, how are you doing? I want to show you more about the compression driver. So I think last time we had the equivalent electrical circuit done. So this time we'll take this electrical circuit and with it we will plot the impedance of this compression driver, and we will see how the impedance varies versus some of the input parameters. So we can identify on this circuit the electrical, mechanical and acoustical side. What we need to do to plot the impedance is to move everything on the electrical side. So we will begin by moving the acoustical side to mechanical side, and then the mechanical side into electrical side. You will see these transformers here and a gyrator here. The gyrator is basically BL. BL, that's the motor force factor, but more accurately we can say it's the coupling between the electrical and the mechanical. The bigger the BL, the stronger the coupling, which means if you have a strong coupling, to get some effect in the mechanical side, you won't need such a big electrical force. Then this transformer from the mechanical to acoustical side, this is the coupler between these two domains, and this is basically the surface radiating, or the vibrating surface, better said. So the surface of the diaphragm vibrates, and this surface couples to the air, and this is the actual mechanical to acoustic coupling factor. Usually it's marked as SD. Of course, for a compression factor, the diaphragm vibrates into a specific acoustic network, let's call it like that, right? So the back of the diaphragm vibrates into an enclosed volume of air here. So this is the back one, and I've marked it as a unknown impedance, ZAB, right? So that's impedance acoustic back. The front of the diaphragm is a little bit different. It vibrates into this small space between the diaphragm and the phase plug. So we have a bit of a compliance there, which is marked as CAF, right? So compliance acoustic front. But some of the air will move through the slits of the phase plug. So this will behave like a mass, that mass of air that is moved through the slit by the vibrating diaphragm. So this is modeled as a MAF, mass acoustic front. And this then couples to another transformer represented by the actual profile of the slit into the throat of the horn. And then we will have the radiation impedance. This is a little bit more complex, and the radiation impedance varies a lot depending on the frequency. So we will keep it just as ZAR. The back of the diaphragm, for now, just for our impedance calculation, we'll just mark it as compliance. So we'll just put it as CAB. Of course, depending on its geometry, the back chamber is usually has it's like a disc, like a hockey puck, if you think about it, right? So the length, the length that extends towards the back is shorter than the actual diameter, right? So because of that, it's not exactly a compliance. Plus, a lot of the drivers will have some sort of sound absorbing material inside that chamber. which again will complicate this network here. But for now, let's just keep it like this. So what we want to do first, we want to eliminate these two. So we're going to eliminate this one, we're going to bring everything here. The way we do this is basically CAB will become CMB, compliance mechanical back, and then these three elements remain the same, and then these two come in the mechanical side as compliance mechanical front and mass mechanical front, and then we will have a transformation to the radiation impedance from SD to ST. ST means the phase plug entrance surface area. Once we've done this, now we can bring everything into the electrical side. Of course, we can eliminate this as well, right? So we can just eliminate this here, and then instead of acoustical impedance, we'll put a mechanical impedance here. Alright, something like this. Now, when we move it on the electrical side, we don't have a transformer here, we have a gyrator, so the transformation will be a little bit more complicated, because series elements will become parallel on the electrical side, and parallel elements will become series elements, and the reactive components, they switch their character once going through the gyrator. So an inductance will become a capacitance, and a capacitance will become an inductance. So I've already done it here. Of course, the electrical ones will remain the same. And then we're going to move CMB. It's a series, so it will become a parallel component. It's a capacitor, becomes an inductance. Resistors remain the same, except they become parallel from series and series from parallel. So this is RES, and this is gonna be the mass component, of course, as a capacitor. Then the inductance here corresponds to CMS. This corresponds to CMF, and this one corresponds to the NF, and ZAR will remain the same because it's just the termination there. So now all we have to do is just apply circuit theorem to calculate the equivalent total impedance of the circuit. So we will have a generator here, right? So basically between point A and point B, what we want to do is represent it as a total impedance. So we can do this very simply with LT Spice, for example. It's free software. You can put in this circuit and calculate the impedance, plot the impedance, or you can use I like Scilab. Again, it's a free software that you can actually script this thing and calculate it and vary all sorts of parameters. I like that more as opposed to Spice, because with Spice it's going to be very difficult to simulate components that vary with frequency. So for example, it's going to be difficult to do. They usually use lamp components, but if you do it analytically, and basically that formula you put it into a computational software, then you can vary parameters within that formula, and you get better result, in the sense that you can try more things and see how it affects the impedance and all that. So let's go to the computer and try it out. Okay, so I had a low-cost Chinese diaphragm for it's a 4-inch diaphragm that I could butcher in order to measure its weight, the compliance, RE, and so the DC resistance and the inductance, and the values I got with this one. So the MMD was around 4.4 grams, CMS is around 0.03 millimeters per Newton, RE 3.655 ohms, and LE is 0.1415. This is at 10 kilohertz, so it's not a very good diaphragm, but it's just for our development is a good set of numbers that we can work with. The hardest one to get is the actual CMS. So what I did is I created a little magnetic circuit and placed this in a magnetic circuit, and if you run an impedance sweep, you will see the resonance. Once you find the resonance, which I think was around 400 hertz, don't remember exact number, but yeah, with a 400 hertz resonance, and you know the mass because you can weight it on a precision scale, then you can easily determine CMS values. Right, variation. So right, so in Scilab here you can open the script that I will link to you, and in the first part of the script you will see a list of parameters. These parameters we can adjust depending on our input data. So what kind of diaphragm you're going to use in this compression driver, this data we can add in here. So as I've shown, I think before, we have a decent DC resistance, we have an inductance, not impedance here, inductance, okay, a BL value, in this case a desired BL value, the product of a desired B flux, magnetic flux density B, and the length of wire that we have on our diaphragm, mass of the diaphragm, the compliance, RMS, and so on. So once we have these parameters written down, this script will produce two graphs. One is the impedance versus a BL, so we will vary BL from one value to another, and we will plot the actual impedance curve as it is modified by the BL parameter. And the second graph is impedance versus the volume of the back chamber. So again we will do a sort of a sweep of this volume from one value to another, and we will see how the impedance changes. And the reason why this is important is that we would like, of course, in our design to reach a specific goal. So for example, if we want to reach a specific resonance frequency, then it's good to know how the back chamber is gonna modify this resonance frequency. So the actual physical dimensions of the back chamber will modify the resonance frequency of the system. And BL, you will see it modifies, of course, the Q. So it is also important. Usually it's safe to say that the higher BL you have, the better, because then you can maybe increase mass or get away with higher mass, things like this, and still have similar performance. Well, looking at these two functions here, you will see basically that here we're doing the transformations from mechanical to electrical, and then we're calculating the acoustic components, and then we're doing transformations from acoustical to electrical, just as we discussed a little earlier. For both functions we have the same thing, and this is because here we are valuing BL, then here we are varying the back chamber volume, marked as VB. If you guys are going to study this script a little bit more, then we'll probably be able to continue the conversation, but it's just series and parallel transformations of electrical components basically, and at the end I'm calculating the absolute value of, I'm plotting the absolute value of the total impedance as I've shown before between points A and points B. Anyway, once we have our information, I already put the data that I got from my measurements in the script, so what we have to do is just click on run here, and whoop, here we go. We have this nice graphs produced for us. So this is the impedance versus CAB, which is the volume of the back chamber, and this is the impedance versus BL. As you can see, the varying the volume of the back chamber will modify the resonance frequency, but will keep the same Q, and varying BL will keep the same resonance frequency but will modify the Q factor. The high frequency part here is dominated by the LE, so it's not exactly accurate. For this, the model needs to be adjusted, but mostly what you need an impedance for is around the resonance frequency. So another thing it's important to note is that the first graph here, this is done with a BL value of 10, right? So as you can see, it's around 15, so it should be somewhere this one, corresponding to this value here. Actually, let's have a look at our range. So the range is defined here for the back chamber, but because it's in cubic meters, you have to apply some transformation to this value, and here BL is varied between 5 and 20 with an increment of 1, so 5, 6, 7, 8 until 20, so on. And here the same thing, from 1 to 10, 1, 2, 3, 4, 5, 10, and then it's the transformation is applied here to get some cubic meters. That's about it. Next thing we'll do is plotting the acoustic response. So we'll apply some force equations. It's gonna be a little bit more interesting than this impedance stuff. Cheers.